Okay, so in this part 2 of circles, we're going to go over the angle relationships that we have in circles. The next part will go over some of the arc length and arc distances that we have, but we're starting off with angle relationships. So to get us off, we've got our central angle, which is going to be equal to the intercepted arc. So for example, if I come down here and I give you this picture, zoom in a little bit. If I've got a central angle, so I've got angle ABC, we know it's a central angle because the vertex is on the center. Well, in that central angle, it follows that the intercepted arc has the same measure. So if ABC is a central angle, then that means its intercepted arc of AC, that being the space that gets crossed on the circle, will have the same measure, and we would say would also be 40 degrees. Okay, so that's all that idea is right there. Central angle equals intercepted arc. Now in an inscribed angle, it is half the intercepted arc. So if I come down to a similar picture, I've got ABC. I now know it's an inscribed angle because the vertex B is on the circle. Well now, if I'm talking about its intercepted arc, AC over here, instead of it being 40 degrees, the same in a central angle, since it's inscribed, it needs to be, in essence, twice as much, or it's 80 degrees. So the inscribed angle, ABC, is half the intercepted arc of AC. So you get this 1/2 or doubling relationship. Now I want you to realize that any angle with a vertex on the center follows the same rule. So for example, if I move over to the side, suppose I gave you a tangent and a secant line, well this angle right here is still half the intercepted arc, even though it's only kind of like it's only being crossed by one line. Now I didn't mean to draw this secant line right here through the center, so that's a mistake on my part, but since it is through the center, then that tells us two things. One, that means that this piece right here is a radius, which means that the radius meets my tangent at a right angle, and that means that this inscribed angle, because the vertex is on the circle, is still 90 degrees, which means its intercepted arc must be double that, or the intercepted arc must be 180 degrees. That also makes sense because if I have a chord going through the center of a circle, it must be a diameter and cutting my circle in half. So that checks out both ways. In addition to central and inscribed angles, we could have what I'm going to just call angles inside. This is what happens whenever you've got chords that cross each other, diameters cross each other, secant lines cross each other, all kinds of different things. And so say for example, I wanted to talk about this angle 1 right here. Well, in order to do that, I need to look at the sum of its intercepted arcs. And you might be saying, what do you mean by intercepted arcs? And here's the deal. I know that because of vertical angles, this angle 1 and this angle over here must be the same. Because of vertical angles, these two must be the same. However, their arcs clearly aren't the same. BE over here is much bigger than AD. But I know these two angles, because they're across from each other and vertical angles, must be the same. So what I'm going to do is I'm going to take half their sum. So I'm going to take half of AD and half of BE. So suppose over here I made AD 60 degrees and I made BE 100. Then that means the measure of angle 1 is going to be 1/2 the sum, 60 plus 100. So then that would make that 1/2 of 160 or 80 degrees. Okay, so because of the vertical angle piece, I know that those two angles must be the same, and it comes from those sum of those intercepted arcs. Now our fourth angle relationship is what happens when our angle is outside. So for example, the measure of angle C right now is outside of our circle. Well, if the angle's outside, now it's going to be 1/2 the difference of the intercepted arcs. So for example, if I look at this particular picture, I know that one intercepted arc is going to be BD right here. So I've got 1/2. And the other intercepted arc over here is going to be AE. So we've got those two intercepted arcs for angle C, BD and AE. Now, the deal is we know that for our purposes in the geometry world, those arc measures and angle measures should be positive. So we're always going to favor going big minus small. Sometimes there may be contexts where you need negative angle measures. This isn't one of them. So we're just going to automatically go big minus small every time. So say AE I said was 60 degrees and BD, it's kind of small. Actually, it's smaller than I meant to. We'll call 20. So that means if I come over here, 1/2 of the big arc minus the small arc means that I've got 1/2 of 40 degrees, which means angle C is 20 degrees. So we get that relationship that an angle outside is 1/2 the difference of the intercepted arcs. Okay? Now I just want to follow up and say that if we look at this relationship, that means that that's also going to follow if I say have a secant and a tangent. I still have a small arc and a big arc, and I can still do 1/2 big minus small, so that angle relationship holds. Now there's one more just specific example I want to talk about, specifically when you've got two tangents, because you could end up with a problem like this. And a lot of times students struggle with this in terms of figuring out what in the world do I do. So what I want you to think about is this. It seems like I don't have much info or much to go on, but I actually do have enough information. So first up, I need to recognize that barring my imperfect drawing skills, these two lines are tangent lines, so they're touching the circle once, okay? So I know that for a detail. I also know that I've got an angle outside, so if I go back to what would be relationship 4 over here, an angle outside is equal to 1/2 the difference of the intercepted arcs. So I'm going to say angle outside equals 1/2 big arc minus small arc. Okay, and let's see what we can plug in. So we know that the angle outside is 50 degrees. Okay, so I know that detail for sure. I also know that the small arc inside, right here, is x. So I've got that value, no problem. Now that x already gives me a variable, which is an issue, because if I come over here and want to say, well, I don't know how much the big arc is, I don't know, let's call it y. Well, the moment I do that, now I've got two variables and I've only got one equation. That's an issue. But let's come back to our circle. I know that a whole circle is how many degrees all the way around? 360, which means that if I know that this piece is, quote, x degrees, then how much must the rest of my circle be, or the parts over here? Well, if the whole circle is 360, and I've already accounted for x of that, it must be that this remaining piece is 360 minus x. So that means I can come down here and claim that my big arc is 360 minus x. Okay? So we're able to set that all up without needing that additional variable. Now let's do a little cleanup. We've got 50 degrees is equal to 1/2 360 minus 2x. 50 degrees is equal to, I'm going to distribute the 1/2. I've got 180 minus x. And if I add x over and subtract 50, I get that x equals 130 degrees. And if they'd ask for the other arc as well, we could find it, but then that is satisfactory at this point. So just realize that you've got that the whole circle adds up to 360, and that is a trait that you can use again and again and again.